Hey guys, here is my explanation on these operational properties. I want to draw your attention to this introduction down here. And it says it's not convenient to use definition 7.1.1, which that's just the definition of the Laplace transform that you integrate from 0 to infinity of e, you know the formula. So every time we wish to find the Laplace transform of a function, for example, integration by parts, when that's involved, evaluating, say, something like this, e to the t squared sine 3t, many of you know that e to the t and sine 3t takes integration by parts twice, and it wraps around, and you have to add it back, and all of that stuff. So maybe there's an easier way to figure out how do we do these using tricks. And this whole section is about tricks to make our lives a little bit easier. So here we go. The first translation theorem is right here, and it says if you know that the Laplace transform of f of t is big F of s, and a is any real number, then if you Laplace transform e to the at times that little function f of t, what you get is a translation of the transform function. So it normally would be f of s, and f of s minus a, you know, if this is x squared and you did x minus 3 squared, you would just move it over 3. This just shifts, and that's why it's called a translation, because multiplying by e actually shifts the function over in the s domain. The proof's pretty easy. So here is the definition of the Laplace transform. We integrate 0 to infinity, e to the negative st, and then whatever f of t is. But in this time, f of t is e to the at times f of t. So that's right in there. And then all we're doing here is using properties of exponents. We have the same base. I've got a t that I can pull out, and if I do that, I get this right here. But I need a negative there. So why I pause for a second is because for me, if it was negative st plus at, I would pull out the t, and I would make it would be negative s plus a, but I would make it a minus s. They don't have it there. But the reason is because you need a negative with the st, and that s becomes that variable right there. And so here it's an s minus a. So in that case, that's how we get f of s minus a. So it really just shifts it. And then down here at the bottom, I'm not going to go through all of the work, but using those formulas, you know the Laplace transform of t cubed should be 3 factorial over s to the 4th. And so then what does that e to the 5t do? It's just going to shift it to the right 5. And so 3 factorial is 6. Normally it'd be s to the 4th, but because we multiplied it by e to the 5t, and e to the 5t shifts it by 5, then I just write the shifted answer and do it by 5. That's so much easier than needing multiple applications of integration by parts. Same thing here. Without this, you know the Laplace transform of 4t is s over s squared plus 16. So this e to the minus 2t, it should translate it as s minus negative 2. And s minus negative 2 makes it s plus 2, so that's how they get that. So it really is, if it's a positive, it moves it, it's a minus 5, and if it's a minus, it becomes a plus, just like in the way we shift functions. And that's why they're called the translation theorems. This one takes partial fractions, and so here you're going to break it apart into its pieces. And then now we're going to pull back on this. So notice this is the inverse Laplace transform. And when I pull it back, I see that I got an s minus 3 squared. But that s minus 3, that's a translation. So that I don't need to worry about. That's just going to be an e to the 3t by it. But then if I take that out, it's basically 1 over s squared. And that's what you get if you Laplace transform the function t. So in there, I know the 1 over s squared comes from a t, and I know that shift comes from multiplying it by an e to the 3t. And so that's how you kind of figure those out. And I'll let you go over the other one. Then we have an initial value problem. So these are just like what we've been doing. And this is what I would ask you to do, is something like this. This is what we're building for. This is what the Laplace transform is used for. And for all intents and purposes, this is the biggest thing I care about. I will make you inverse Laplace things and Laplace things, but the big part of this and the reason that we've learned all this is to be able to solve these differential equations. So, you know the y double prime Laplace gives you this part. The minus 6 is right here. The Laplace transform of y prime is right there. And 9, the Laplace of y, is right there. This is a t squared, which should come over, it should be 2 factorial over s cubed. But it's multiplied by a 3t, so it should be s minus 3 cubed. And so you can see that right there. Then we proceed exactly like we have in all the other cases. We just solve for y of s, we get this thing, we take it, break it into its pieces, then we inverse Laplace each piece, and all of these are slightly shifted, and so notice they have these e to the 3t's multiplied by it. That's really all that there is. So, and then here's another example for you there. The next cool thing is this. There is something called this Heaviside function, and it looks like it's pronounced heavy, but it really is Heaviside. And it's named after Oliver Heaviside, and so this is his function. And it's a unit step function, and that's why it's a fancy u in there. And the t minus a, that just tells you when it turns on. So, you know, in t minus 5, t minus 9, you know, and all of that for launching rockets. And look, so between 0 and a, this thing is dead stagnant. It actually has an open hole there. But as soon as we hit a, it turns on. Immediately, instantaneous at a, and then it runs out. And so that's what this function is. It's defined to be piecewise. So they go through some of this stuff, and here's the thing. It says when a function f is defined for t greater than 0, and it's multiplied by the unitary function, the function turns off a portion of the graph. And so what does that look like? And so in here, they say, turns off a portion of the graph of that function. For example, consider the function 2t minus 3. To turn off the portion of the graph for 0 to 1, we would simply just form the product this times that unitary function in there, because when you're less than 1, in that case, that would be 1 if that's a 1, anything between 0 and 1 will be 0, and so you will be multiplying, where was it at? You'll be multiplying 0 times this function, and so that's what gives you that 0 right there. And then normally the line would have looked like that, but we didn't turn it on until 1. So at 1 we just light it up and it takes off. And so that's what they're trying to show you in there. This thing's defined everywhere, but this thing is 0 up into a point, and 0 times anything is 0. So it will shut it off for as long as you want, and then it turns it on and lights it up. And so this is how it's used in switches and circuits and electricity and magnetism, and there's numerous applications for this, you guys. The unit step function can be used to write a piecewise function in a more compact form. So if you had a function like this, and like one that I think of all the time is absolute value x. It's defined to be x if x is greater than or equal to 0, and negative x if x is less than 0. And so there is a piecewise function in there. But this you kind of can't compute easy in functions and in equations and stuff like that. You have to do cases where it depends if I'm in this region or if it depends if I'm in that region. But you could write it as just one function, and you could say it's g of t minus g of t times the unitary function of t minus a. What does that do? Well, once we hit before a, this will be 0. And so, from up here, down here, whatever a is, the function's 0. So this will be 0 times it if we're less than a, and this will be 0 also. And so if we're less than a, we're going to have just g of t. Oh, that's what it says. And if we're bigger than a, this becomes 1, and this becomes 1, and g of t times 1 is just 1. So this is g of t minus g of t. That zeroes that out. And since that's 1, we just get h of t times 1. And that's because this thing, when it turns on, it just takes a value of 1. And so you can use that. And now this is a single inline function. And you could actually go through and figure it out from there. Okay, so then they just do some examples in here on how to write it and how to think about it. You should write these, plug in values, figure out that yes, it does what it's supposed to. This here's if you want to turn it on after, and how would you do that? And so the second translation theorem says this. If you know f of s is what you get when you Laplace transform this little f of t, and a is greater than 0, then if you Laplace transform a shifted function on that unitary piece, it's the same as just multiplying by whatever e to the negative as is by the function that you know is the Laplace transform of it. The proof, you can go through and see, we have to break apart, and they're using this additive interval property for integrals. And it says this, that if you integrate a to b of f of x dx, that's, and I'm just going to write on here, let's say this is a and this is b, you'd get all that area there. But if I chose any c in between, I could say, well, that's the same as integrating a to c of f of x dx plus integrating c to b of f of x dx. And what that would do is put a line here, and we'd figure out that area first, plus that area, but that is the entire area that we started with to begin with. So, since that's the case, that's why they're talking about that additive property of the integrals right there. And that's how you know that it's shut off for some point. And so you can figure out what it actually becomes. So, then they go through and they do a few of these using the inverse Laplace, and you can see that there is shifted functions in there. Once you follow this formula right here and you look at these examples, you'll get the idea immediately. So 1 over s minus 4 looks like it came from the function. What function is 1 over s? It's 1, right? So I don't have the sheet right in front of me, but I think when you Laplace transform t, you get 1 over s. And so we have 1 over s minus 4. And so that would come from 1, but then we've shifted it. And so this shift, we need that piece in there to shift it. And because this is attached to it, the e to the minus 2s, notice it's not a t. And so here, when you have it in the s, and notice we're on the s domain right here. That's why it's called, and I think they put it in here, translation on the t-axis, because it turns out that when you multiply stuff in the s domain, back in the other piece, when you inverse Laplace both sides of this, you'll get that function back. And that shifts the function back in the t land. So multiplying by an e in the s world shifts the function back in the t world. The first one was called translation on the s-axis. And notice this one, we're going in the forward direction. We're multiplying by a t now. in the t side, and when we Laplace transform that, that shifts it on the s side. So that's why it's a translation on the s-axis, but the stuff happens in the t domain. So that's why they're called two different things. They're not really different. It's just the way that the math works out in there. So on here, this would come from 1. We need the shift in there from that. And then this e to the minus 2s, it gives us the unitary function on t minus 2. And the weird thing about this, and I said it before, notice if that's a minus a, that's a minus a, and that's a minus a. And so that right there, the sign matches in this. In the first one, if that was a positive a, it became a minus a. So the positives and negatives kind of matter, and you need to really figure out a way to save it in your mind of, if I'm going forward, I call Laplacing going the forward direction. If I multiply by an e to the at, some exponential function, it's going to shift it the way that I think. Like if I want to move it right 3, I'm going to put a t minus 3 or an s minus 3 in there. If I want to move it left, I'll put a plus in there, just like I do with regular functions. But when you get to that second translation theorem, a negative stays, whereas before a negative there would put a plus there. But it doesn't work that way. And so that's why we have that right there. This would have came from some sort of a cosine, and that cosine, it'd be cosine 3t normally, but that cosine 3t has been shifted by pi over 2. So there's the shift, and then it adds the unitary function. That's this piece right in here. Because when I Laplace both sides, I should just get that function back. So that's how these actually work out. Then they just show you a few transforms going either way in there. And I won't ask you like actual word problems, but I did tell you down here, these are cool just to kind of play with. These are all Laplacing the forward way, translating on the s-axis. These are coming back the other way, but these are still, I think, translations on the s-axis because we don't have e's over in the s domain side. So it's not translation on the t-axis, it's only the s-axis. These are what I would ask you to do. So anything in here is what I would ask you about. And then here's the ones on the t-axis. And so if you want to practice those, this is going what I call the forward direction up in this set. And then these are going the backwards direction, and so on and so forth. But it is fairly self-explanatory. It is on the sheet that I gave you. It's in the book. Like any book that has the Laplace transform will have Laplace transforms of derivatives and Laplace transforms using the translations, because they come up a lot, because you don't always flip a switch right at time 0. Sometimes you wait a few seconds, you wait an hour and turn it back on, and you want to know what happens. And so in that case, we'd like to have a way to incorporate into the mathematics the turning on and off of certain things. And it's cool that this unitary function, with our understanding, will do exactly what we think it will. So I'm going to stop there. Hopefully that's enough, and you can read this. And I know I went over it fast. Part of it I still am not feeling 100%, but and I told in one of my other classes I'm going to make their other video tomorrow, but that's just because I wanted to for sure get you yours, and I have one more to do for another class. And you can see at the top of this, it is 5:30 at night, and this is all I've been doing all day. But it's what I love, so I'm happy to do it, but my voice is starting to go. So I'm going to cut it short here, and if people show up to office hour and they've watched it and they say you need more or something like that, I'll do more, and I'll flip to a notebook, and we'll actually work out problems, and we'll not just explain out of the book or whatever. So Anyway, hang in there, guys. Take care. Keep plugging along. I'm proud of you, and we'll see you soon. All right. Bye bye.